the digital electronics and circuits and some of the number system related to this. And in the previous class, we have seen that another very interesting number system and very useful number system could be hexadecimal number system, where we have base value as 16 or radix equal to 16. So because it is 16 and we have to express these numbers as one digit in this number system. So apart from taking 0 to 9, the numerals, then we can take help of some letters or alphabets. So from A to F, we have taken and assigned some values. So A means 10 and so on, and we go for up to F, which signifies 50. So the maximum number could be only R minus 1, which is 15. And these numbers, all from 0 to 15, we can express in terms of 4-bit digits. That's why the 4 bits are clubbed together to form one hexadecimal digit. So this is what comfortably we can write or assign or represent. Now we have seen how to convert any binary number to a hexadecimal number. So always the rule is start from the least significant bit and keep clubbing the 4 bits together, and you will have the hexadecimal number. So if you have any shortage of bits on the most significant bit side, then you can add few 0 bits at the end, and then you can club and write the number. So this is what we have seen. Then reverse, we have seen that it is very easy to do, and it doesn't matter whether you start from the most significant bit or least significant bit. When you are going from octal or hexadecimal system to binary, then you can take any number and just represent that in the corresponding binary. So you know that if it is hexadecimal number, then each and every digit, hexadecimal digit, is made up of 4 bits of the binary. So you can express separately, and this is perfectly all right. Similarly, for the octal number system also, each and every octal digit is actually made up of 3 digits of binary. So each and every octal digit can be independently expressed in terms of binary numbers like this. So this is very straightforward, and this has advantages. Let us say when we go for higher order, higher number systems and all. So the advantage is that if we have a bigger decimal number, let us say, and we want to convert it to binary, the direct conversion may take a lot of steps and it could be very lengthy. Even for computers also, it may take a lot of time and resource. Whereas if you have the means to convert it to hexadecimal number or any other higher number system, and then you can go back to binary, that will be pretty simple and straightforward step. So number of steps will reduce. These are the advantages. And yes, the hexadecimal number is kind of most used nowadays if you talk about the programming languages for the digital circuits or any other system where we are representing all our binary numbers and all. Hexadecimal is a very convenient way and is universally accepted. So whether we take 16-bit numbers or we take 32-bit numbers, these are all different things, but all are expressed in terms of hexadecimal numbers. So we have different definitions for what we call a 16-bit number, what we call a 32-bit number. That all comes with the language when you start learning the hardware description language, but essentially all these are represented in terms of the hexadecimal. So this is what the understanding is. And now when we have, let us say, any hexadecimal number or any octal number, and we want to convert it back to the decimal system, we need not go back to binary and then come over here. We can as well follow the standard rule of converting it to the natural radix, which is R equal to 10. So this formula is always correct as long as you are following the rules while making this number system. This is correct. Now we can represent, let us say we have the numbers. So quickly we can make a table. Let's say we have decimal numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 would become A, or no, here let me write 10. So these numbers, if you want to express, let us say in terms of octal numbers and in terms of hexadecimal numbers, so and let us say string of few bits, let us say 3-bit string, which means what? It has 3 bits. So 0 can be represented as 000. This is binary, 3-bit string of binary number. Then there could be 4-bit string for binary number. So this could be 0000. Then we can have the octal number system. Then we can have the hexadecimal number system. So without crossing the limits, let us say when we are saying octal, we are of course talking about only 1 digit. Hexadecimal, 1 digit only. So without crossing these limits, how many numbers we can express if you see? So with 3-bit string, we can go up to 7, so which is 111. Beyond that, we cannot express. That is what we have seen, the limit of this. So it will overflow, it will go back to this 000, which means representing 8 is not possible with 3-bit string. And same with the octal. If you have only 1 digit, you can go up to only 7. So 0, 1, 2 and so on up to 7, that's all. Whereas if you take 4-bit string, you can cross this boundary. So you have enough number of bits available and maximum you can go up to 15. So total 16 numbers or 16 decimal numbers you can express. So here in octal this is all not possible, and same with hex. So this is what we have learned. We are clubbing these and making this. So this 0, 1, 2 and up to 7, and then it goes on 8, and then we have 9, A, B, C, D, E, F. So that is how we can tabulate or summarize whatever we have done so far up to this hexadecimal number system. So these are the limitations and these are the properties we can say of all these number systems. We will come across some other number systems as well. So before that, what other thing we learned in yesterday's class is how to represent a negative number. So we have seen that always there is a symbol and there is some magnitude associated with the numbers if you want to represent the positive and negative, both the numbers, similar to vector where we have a direction and magnitude. So of course, when we have this kind of arrangement, we may have 2 possibilities for 0, but each giving the unique value, which is not necessary that we must have, but we may have in any number system. So we saw that if let us say we take some arbitrary number system similar to what we have seen just now. So here we can assign the most significant bit as the sign bit. So which means we will not take the value of this bit. We will only consider the sign, whether it is 0 or whether it is 1. We are not bothered about what is the weightage of this bit or what is the value associated with it, but only the sign which is associated with this bit. And rest of the bits are used as it is, as we have learned for the binary system. So this could be one way to represent the negative numbers. So we have the better ways of doing this. So that is where we started understanding the complementary number system. So complementary number system signifies that if you have number x and you add its complementary to itself, then the result must be 0. This is what the basic meaning of complementary number system. And we have seen there are 2 ways of having the complementary number system. We can go by radix complementary, where the complementary number is defined like this: r raised to the power n minus 2. So all the properties what we are discussing over here for the complementary system must be valid in our definition. So we tried to see that if we have a decimal number system with 4 digits, 1849, and we try to get the complementary, 8151 is the complementary of this number in the 4-digit system for the decimal number. So if you add, you will get the result 10,000. So of course, when we are taking only 4 significant bits, the 1 is kind of overflow, we will ignore that, and so we have the property fulfilled. The condition is fulfilled. So yes, we are going on the correct track. So similarly, if you try to take the complementary of 0, you will end up having 10,000, and actually leaving the last bit, we have the correct value. So here we say that we have unique representation for 0. So when we have unique representation for 0, then of course our number of negative and positive numbers are little unbalanced, because total numbers what we can have is 10 raised to the power n or r raised to the power n. So if only one 0 representation is there, that means we are left out with this. So always the negative numbers are one more. So negative number would be this. Okay, just let me check. So there is slight imbalance. That's what we need to keep in mind. So okay, I think, I don't know where I have written. Fine, I'll clarify it later on. So it's okay. That's not very critical that we cannot have this thing. The only issue is what I want to point out. Let us say there would be one negative number which will not have any complementary positive number. That is the meaning of saying this. So there would be existing one negative number in this number system which will not have any complementary positive number. That is all I want to convey in this. So I will tell what is the range and how it goes. So just because we have only 1 0, that is why we have unbalance. We have the positive number 1 less than the negative numbers. That's all. Nothing so critical about this. So we have seen that, okay, if you are trying to come up with the radix complement, then another way to do is to express it in a little better manner and take the difference of the number in this manner. You subtract it from all the highest integers possible in the number system and then add 1. This is the easier way to do compared to what we are doing, like taking the difference directly. So of course the result will be same. So whatever we have seen, the 1849 at base 10, now we are doing in the other manner and we are coming up with the same result. Okay, so now once we have this radix complement system, we can have specific cases. Let us say r equal to 10. So in that case we will call it 10's complement. So we have seen how it works, and we have r equal to 2. If we are dealing with the binary number system, then we will call it 2's complement. So that is how the definition goes. That is how the terminologies are defined and people follow. But the essence is same. So we are doing the process in an exactly similar way. And when we are representing binary, we do not say that this bit is only sign compared to what we had earlier. In the first cut, when we were seeing the positive negative numbers, we said that okay, this is one possibility. We can say the most significant bit is either plus or minus. But here we can actually have value associated with this, and this value could be minus of 2 raised to the power n minus 1, which means all other bits are following the same weightage, the natural weightage whatever is given, except the last bit which is having a negative weightage, so minus of 2 raised to the power n minus 1. And if you solve, you will come back to exact negative value of this number. And you can add and see that they will end up giving the 0. So this is what we have seen for the 2's complement or radix complement system. Then we have the diminished radix complementary system or complement system. So here nothing, we are not adding that plus 1 which was extra there in the radix system, and this is even simpler. You need to only subtract from the highest possible integer in that number system, and your complement number is there. So again, it must follow the rule. It must follow that d plus d complement must add up to 0. But here one catch is there. The representation for 0 is not unique. Representation for 0 could have two possibilities. Either it could be 0000 or the highest possible integer in that number system, 9999 or 1111, whatever number system you are considering. So these both extremes actually represent the magnitude 0. So this is what we have to keep in mind while doing the diminished radix complement system. So of course, diminished radix, when we talk about the particular cases r equal to 10, then it is 9's complement. It is called 9's complement. And when we talk about binary number system, it is called 1's complement. Similarly, we can have for octal number system or hexadecimal number system also, we can call it 16's complement or 15's complement in case of hexadecimal. For octal, we can say 8's complement or 7's complement in case of octal. So that is how the definitions would evolve. So even for any common or any given radix system R, you must know what is the meaning of radix complement and diminished radix complement, what we are referring to. This is what you have to understand. So
in any number system, how can the extreme maximum number systems are like 999 can represent 0?
Which is what I was saying last time, no? See, this is not something we are telling in a common number system, our decimal number system, that the magnitude is going in a linear fashion. This is what I drew over here. When we have both the positive and negative numbers to represent, the magnitude doesn't uniformly increase always. Understanding my point? How can you represent? You have the fixed number of bits, let us say 4 bits given over here. You have to represent all possibilities for these numbers, including the positive and negative numbers. So you must have a way to represent that. Understanding my point?
Yes, sir. But in this case, sir, like I'm getting the point. Like, sir, for radix 10, and we have the number of bits 4. Then we can the maximum number we can represent is 999.
Yes.
So and if we add 1 to it, we'll again get 0. But sir, how did 999 represents 0? Like we are saying.
I'm saying, see, number system by definition is saying what? If you have any number, you take the complement, add both together, the sum must be 0. This is the definition. Now, for any radix system, you try taking the complement of 0000. For the radix complement system, you will exactly get 0000. For the diminished radix system, you will get that mm or 9999 or 1111. So by definition, this is 0. Understanding my point?
Okay, sir.
This is by definition we are saying that this is 0 because it has to fulfill this. Otherwise, this whole thing would be wrong.
Okay.
Clear? Now, let us go to some different numbers. So this thing you have to understand that when we are representing both positive and negative numbers, it is not uniformly increasing. And that is what the weightage, what we say that minus 2 raised to the power n minus 1 for the last bit. This weightage we have given, right? This is what matters. This is for the radix system. For diminished radix system, the weightage is just 1 less, I feel. I mean, in terms of magnitude. So it is.
There are two systems to follow, sir. Now we can follow one of them.
Yes, yes.
Okay.
And more universally accepted system is actually radix complement system. So need not worry, you can as well follow whichever comes in front of you, but we should know all. There is no harm in knowing anything, right? So here the magnitude for the most significant bit for the diminished radix system is minus of 2 raised to the power n minus 1 minus 1. That's all. That is the difference from radix complement system to diminished radix complement system. The most significant bit is weighted here as minus 1. For the radix complement system, it was minus of 2 raised to the power n minus 1. That's all. This is the only difference. So basically what any person who has designed is trying to say is that if you keep this weightage and you write all the expand the number system, you will exactly get the negative value of that number in the decimal system. That is why all these adjustments they do. That is all. Nothing so special about this. If you are having like what we saw, if you have 17 expressed as binary number system and you take the complement of that, the value must be minus 17 in decimal. So that is why we say that if you take MSP as this, you will end up having this value in the decimal system. That is all. Clear? Is that fine?
Yes, sir.
Yes.
Sir, I have a doubt.
Okay. So
Sir,
now let us
excuse me,
see
sir.
something. Yeah.
Sir, in the graph, the value of 7FFF was the middlemost value.
Yeah.
Sir, so was it positive or negative, like it is in the middle?
No, it's here. 7FFF is here.
Okay, okay. Sir.
See, 7FFF is actually what? Everything is 1 except the most significant bit. 0, 1, 1, 1, and then 1, 1, 1, 1. Sorry, 4, 1, 1, 1, 1, 1, 1, 1, 1. So obviously, even if you take this weightage as suggested by the radix or diminished radix complement system, this will be the maximum possible positive number in the number system. The moment you go next, it is 1 and all zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is the most negative number because it's only 2 raised to the power n minus 1 or minus 2 raised to the power n minus 1 minus 1. Understanding my point? So that is why I say it is here. Immediate next number would be here at the extreme negative. So there is jump from the maximum value to this value. Fine?
Yes, sir.
Okay. Now, few more things let us try to understand. See, when we are talking about different number systems, there are few more which are used, not so often, but yeah, sometimes people use in their systems, and it's not very, there is no strong reason why we should have that in our number system, but sometimes they give certain advantages, and that is why those are followed. So one such thing is binary coded decimal. So by definition, you can say binary coded decimal means what? The decimal numbers we are having as binary numbers, but not by the usual conversion, but as a code. What is meaning of code? by rule that we say if this is the number which represents this particular decimal number, then that's all. We may not have any specific reason why this is so. Understanding my point? So sometimes it will follow the usual rule also, whatever weighted representation we have seen so far, it may follow, but that's not necessary. It may have different weightage also. Some modified weighted system also could be there, or something different could be there. But each one of this has some advantage, and that is why sometimes we learn those things. So one such thing is binary coded decimal. So when we say binary coded decimal, the most straightforward number system is the same as what we have followed so far, which means you convert all these. So how many decimal numbers are there? We are talking about only this 0 to 9. Anything more than this can be expressed in terms of as combination of all this. So if we can express these, then we can express any other number as combination, isn't it? So this is our decimal. Now the BCD number says that you have the usual way of conversion. So how many bits would be needed to express these numbers if you have to convert to binary?
Four bits.
Yes.
All.
So 4 bits would be needed. What will happen? You start from 0000, 0001, 0010, and so on. Keep going, and you will end up to what? 1001. That's all. Now the remaining all 6 more options are redundant. They are not used in this. They are not useful for this BCD number system, because we are trying to represent only these 10 decimal numbers in terms of the binary coded decimal. This is the code for 9. This is the code for 8, 1000. Understanding my point? Okay, so sometimes what happens, let us say, people design systems where they are entering the decimal numbers as input, and the output also they want directly as decimal number. So that's why these are coded. So when you have these kind of coded circuits, the moment you enter any decimal number, it will be read as binary, something like this. And all the operations can happen in the binary system, and then final output also will be code this compared with the code that it corresponds to what, and then the decimal output would be given. Understanding my point? Yes or no?
Yes, sir.
Yes.
There is nothing so special about this particular binary coded decimal number system, but there is something more. Now, if let us say I tell you the weightage followed for this number system is, that is the natural 8421, which means the weightage for this MSB is 8, for this next number is 4, for the next bit is 2, and the next bit is last bit is 1. This is the weightage followed in this number system, right? Understanding my point? Now we may have any other weightage. Let us say someone says that, okay, I want to have a weightage of 2421 instead of 8421. You understand meaning of this 2421?
Yes, sir.
Which means the MSB will not have the regular weightage 2 raised to the power n, something like that. No, n minus 1, no, something not like this. But what we decide, we say that MSB has a weightage of only 2. The next digit has only weightage of 4. And the next one has 2. The next one has 1. Understanding my point? Then this also could be a coded decimal system where we can represent all our numbers in this manner. Of course, here when we are changing the weightage, it may happen that the same number may have 2 different ways to represent. But once we fix the code that, okay, we are, for example, if you come to 5, then 5 can be represented like 0101, or it can be represented like 1010. Both are 5, right, in this system? Yes or no?
Sir, 1011.
Okay, yes, 101. So both are actually representing 5 if you convert it to natural system. But we will say that, okay, we will take only one. Let us say, I think they are considering 1011 or 1001. Yeah, 1011 they are following. So this thing they discard, which means this is not part of code. Understanding my point? So there could be no logic why we are following this and not this. This is how it is defined. This is how the person who is designing this particular code is saying that I want to follow this. Now, what is the advantage if we are following this? Let us see. So let me first write. Then we will see the advantage as well. So up to this, it is all same as this BCD number system. The moment you go to 5, it changes. We represent it like this. And then 6 becomes like this. And then we have 7. Then we have 8. And then we have 9. Now if you see, we have seen the complementary system, right? In this decimal system, if you take 9's complement, so what is complement of 0 is 9, isn't it? And vice versa. What is complement of 1 is 8, isn't it? Yes or no?
Yes, sir.
Yes, sir.
Now here if you see, it will match 1 to 1. The complement of this would be this number, 1's complement. So exactly you just change the zeros with 1's or 1's with zeros and you will get the complement, the complementary number. So this is how, when they see that yes, some advantage I am getting by this definition. So this 4 and 5, that is why 5 is represented like this, in this fashion, because 4 and 5 are 1's complement of each other. Understanding my point? So this is how the advantages are seen and then the codes are defined. This will not be seen in this binary coded decimal. You cannot say that 0 is complement of this. This is not true. But here it's correct. Understanding my point? So we may also have some other way. Let us say we may have 4221 code, or we may have something, but we must have way to represent 9. If you say 2221, then you are short of numbers. The weightage is not sufficient to define or to accommodate 9 numbers. So somehow we should have the way to accommodate all 9 digits. So we can have some combination of this 42221 or 2241 or 1224, whatever suits our requirement, whatever suits our system, we can define. And we can simplify our logic, we can simplify our operation, our digital circuit using these kind of combinations. So one such thing I have shown over here, and the advantages also we are seeing. If someone is, let us say, very much doing the complement of something, that process is involved so much, so many times it is repeating, then it is better to go by this way. You can keep taking 1's complement, you would be knowing where you are floating, isn't it? So that is how this number system goes. Now there could be another one. And again, when you say like what are the advantages, straight away you will not see any advantage of this. So this is called XS3. XS3 means what? You add 3 to all these numbers. Whatever you have generated as BCD, just add 3, and 3 in the digital sense or the binary sense. So add, let me write in different color, you add 0011, that is all, to all the numbers, and then whatever you get, this becomes another 4. This is called XS3 code. So if I write all the numbers again, 0011, 0100, 0101, then 0110, 0111, 1000, 1001, 1010, 1011, 1100, and that's all. So we have represented all the numbers. Now you will be surprised to see there is no 0000 in this number system. You are representing 0 with this 0011. Understanding my point? Sometimes when we have the possibility that there are chances of error which people may make, or sometimes some other possibilities are there which may create change in the values of all these bits, then we may adopt some different kind of codes or different kind of systems where we can have a check over all this. Understanding my point? And again, this also has the property of this ones complement, what we saw in the 2421 system. So here again, 0011 is complement of 1100. 0100 is complement of 1011. All these ones complement. So these properties also it is following. So these are different systems, different codes which we follow sometimes depending on the requirement. Am I clear? So let me see what else is remaining. Okay, so now another thing to understand when we are dealing with such kind of codes, what we have to understand that any arithmetic operation, if we are doing, up to this it is clear, right? There is no confusion. Yes or no? Yes or no? What? 111 people, no response. Yes or no? Then I'll proceed further.
Sir.
Okay.
Yes,
sir.
Yeah, you should be awake at least, if not attentive. That's what my request is. So now when we talk about arithmetic, let us say we are adding two binary coded decimal numbers. So when we are adding, we must end up with another binary coded decimal number only. We should not change it. We should not go to something else. It should not become something else other than this number system. For example, if you add 4 and 5, the result would be 9, isn't it? So how are you representing 4? 0, 1, 0, 0 and 5, 0, 1, 0, 1. Is that correct? Yes or no?
yes, sir. Yes.
And 9 you are representing 1001. All this is part of your binary coded decimal system. All the three are part of this. But now if you have to add 9 into 5, if you have to add these two numbers, it will become 14. So now let us see what is happening over here. 9 is what? What is the code for this 1001? What is the code for 50101? Now if you add, what you will end up with 0, 1, then 1, 1. Isn't it? This is actually the binary conversion of 14. Isn't it? But is it part of this BCD number system? What you have defined, you have the maximum representation over here. Anything beyond that is not part of BCD. Understanding my point?
Yes, sir.
So let us understand from here what is happening. In the decimal system also, if we have only one digit to represent, what will happen to this digit? This is a kind of carry. So you can say this is nothing but 10 plus 4. So when you add this and you have only one significant bit to represent, you must end up coming to 4. You are going in that cycle 0 to 9 and then you come back. You are counting in that only. Anything coming other than that will be part of next digit what you are putting. That is carry forward for the next digit. It's not for this digit. Understanding my point? Similar arrangement we have to make over here also. That when we are representing BCD with 4 bits, it must remain within the BCD representation and anything left over must go for the higher bit. Go for the next higher BCD representation for the decimal number. So what you do, you simply add 6 to this number and what you will end up having this. Now what is this number? This is 4. Same as your result what you are getting in decimal. And the extra carry what you have generated, that will be shifted to what? The next higher BCD. Understanding my point? Getting my point or not? No, these are different blocks. You can say this is least significant bit. This is most significant bit. So any operation happening over here must not change this number system. No, if you are following BCD, the least significant bit must remain in BCD. Rest, whatever carry you are generating will go to next. Again, with this keeping in the BCD, whatever it generates will go to next. So this is the way you can come back to your number system while generating a carry forward for the next digit or next bit. Understanding my point? So this is kind of correction we have whenever we are doing arithmetic system with these kind of number systems. Now why 6? Does that not come to your mind? Why 6? Why not any other number? Yeah, any response?
Sir, because 6
4-bit
numbers are
system
not
we have
used.
16
Hmm?
and in decimal there are 10, so we need to add 6.
Yes. So total there are some 16 possibilities of which 10 we are utilizing. So the remaining 6 we have to somehow pass through. We have to go forward by 6 more numbers. So 6 we are adding. That's all. We have to somehow cross over 6 more numbers. That's all. Nothing much in this. So this now here I stop all the number systems and all that. There are some more Hamming code and all that, parity check codes and all. I think it's not very crucial that you must know, but if you are really interested, you can read on your own. You can discuss sometime later on if you find it really useful for your things. But I think up to this it is fine. You have fairly understood what all number systems are possible and what all things are there which we should understand or we should perceive in a different manner. So some things are following your usual decimal number system routine. Some things are not following that routine. So it's okay. We have all the possibilities over there in the digital domain. Now, going ahead, we will discuss some of the things related to this switching algebra, or that is called as Boolean algebra. So, meaning to say there must be some rule when you want to perform some of the arithmetic operations, you must have some rule. And of course, because this is quite different from our decimal number system, so it cannot follow all the things. It will follow few things from our natural decimal system and all the existing conditions and postulates and theorems, but not all. So some are specifically true for only this kind of systems where we have only 0 and 1. These are the possibilities for the bit, for the number. Anything other than this is not possible. and both cannot happen simultaneously. So the first and foremost rule, we must know that if x is not equal to 0, then x is equal to 1. This is if x is a Boolean variable or switching variable or whatever you want to say. Similarly, if x is not 1, then only x is 0, which means it cannot take both the values together. There is no averaging, there is no having any in-between value or any other thing. Any ambiguity is not there. It is either 0 or 1, very, very clearly. So this will be the most important rule on which all this will be based on. Clear? So from this we will start in the next class. And any questions, any doubts, if you have, you may ask now. Then we can stop the class over here.